Assalamualaikum, my name is FATIN AUNI binti PISAL, matrix number AD190185, and I will explain about the introduction to the deflections of cantilever beam. Cantilever beam is a type of a structural element that is anchored at one end and extend out into space. When the load is applied to the free end of the cantilever beam, it will experience a deflection or bending due to the force of the load. The amount of deflection is determined by the property of the beam, including its length, cross-sectional area, and material property, as well as the magnitude and the position of the applied load. Engineers use mathematical formula and computed models to calculate the deflections of cantilever beam in order to design safe and efficient structure. Before calculating the deflections of the beam, the second moment of area of a beam is needed to be calculated, and after that we can calculate the theoretical value of deflections of the beam using the Macaulay method. But the Macaulay method is modified into the stated formula below. Thank you.
Good morning, everyone. My name is CHENG with the metric number of AD190211. Next, we go for the observation of the experiment. Firstly, both ends of the mouse steel, brass and aluminium are attached at the beam apparatus. Then hang the hanger without load, and all gauges is adjusted to 0. Then, we apply the load of the hanger from 5 Newton to 30 Newton, and the rating of the gauges F and E is recorded. From the results, it shows that the increase and decrease column for all the three materials have a linear increasing data. And theoretically, mouse steel has the slightest deflection, and the aluminium has the largest deflection when 5 Newton of load is applied.
Hi, my name is Chuan. I would like to proceed to the part of the result. For the result obtained, they are tabulated in table 1, and for the specimen of brass, aluminium and mouse steel, they have the same length, thickness and width and the I value. Their length are 600 mm, thickness is 6 mm, their weight are 18 mm, and the I value are 3.24 times 10 power of -10. Next, I would like to proceed to the table 2, which is the deflection at x is equal to L divided by 4. For the specimen of brass, the least average deflection is 0.47 meter, while the load is 5 Newton. The greatest average deflection is 2.03 meter, while the load is 30 Newton. For the specimen of aluminium, the least average deflection is 0.47, while the load is 5 Newton, and the greatest average deflection is 2.12 meter, while the load is 30 Newton. For the mouse steel, the least average deflection is 0.43 meter, while the load is 5 Newton, and the greatest deflection is 1.02 meter, while the load is 30 Newton. Next, I'd like to proceed to the table 3, which is the supporting force as x is equal to L. For the specimen of brass, the least average deflection is 0.76 meter, while the load is 5 Newton, and the greatest average deflection is 3.46 meter, while the load is 30 Newton. For the aluminium and mouse steel, the least average deflection is 0.77 meter and 1.11 meter, while the load applied is 5 Newton. For the greatest average deflection for the aluminium and mouse steel are 5.02 and 5.82, while the load applied is 30 Newton. Based on the result obtained, it shows a linear increasing data for the increase and decrease data for all the material of beam. And that's all from my presentation. Thank you.
Hi, my name is ARBAIN FITRI. In this video, I will explain about the discussion of this lab report. Okay, the specimen, in this case, we use brass, aluminium and mild steel have their result based on his experiment. Plot in the form of graph. In essence, all the graphs display as a linear increasing trend. This indicates that the deflection of specimen does, in fact, increase with additional load when they test experimentally. Hence, it can be said the deflection is directly proportional to the load. Okay, when comparing the deflection between all these three specimens, brass, aluminium and mild steel, we found that the mild steel is the stiff, followed by brass and lastly aluminium. Okay, this is because mild steel has the lowest deflection compared to the brass and aluminium. Mild steel has the highest Young modulus among the three of other material, which indicate the highest the Young modulus, the highest the stiffness of the material, and thus the less it will defect. Okay, mild steel Young modulus is followed by brass, then aluminium, which is completely proof, the graph drawn. Okay, next, by observing the graph of load against deflection of the experimental and theoretical value of specimen, it's seen there is something varied between them. However, the difference between the experiment and theoretical value are almost the same. It noticed that the theoretical value has more deflection compared to the experimental value, but lower load of 5 and 10 Newton. Okay, this is clearly show better handling and setting up the apparatus during the experiment is crucial, since a bit of deviation might change or alter the value. However, this might also be caused by apparatus in place, such as the diagnosis. Systematic error can always occur when the apparatus is not maintained or recalibrated for a long time. In this scenario, the diagnosis might be required to recalibrate to get the more precise value. The gradient of the graph can be used to find the theoretical value of Young modulus for its specimen. It can be observed that there is a huge difference in gradient in the graph of load versus deflection of mild steel specimen, which is 63.7%. In general, this can be caused by some human error during the conduction of experiment, such as making sure the beam was parallel by using the water level ruler. It could be possible that the load was not placed tight, or the load was not right position, as slight variance in placement may cause great difference because theoretical and experimental value at highest load. The important to know the characteristic of mechanical behavior of engineering component in material selection. First, failure do arise because of error in material selection. An engineer must figure out what is needed in certain part, such as what is in the budget, load, tensile strength needed, or even the elasticity of the material. Second, the lifespan of the material. The condition that a component is working in may cause it to fail, as certain material may not be able to survive very long and succumb to rust, increased aging, and corrosion. Okay, that's all from me. Thank you.
Hi, I'm DINESH MANOHKARAN. Let me proceed with the conclusion. In deflection of a cantilever, aluminium beam has the largest deflection, followed by brass beam and steel beam. The beam deflection is directly proportional to mass applied to the beam. The higher the modulus of material, the smaller the gradient of the line for each graph. The equation predicted the behavior of beam which is in relationship. The theoretical deflection. In deflection of a simply supported beam, aluminium beam has significantly less deflection in simply supported beam than cantilever. Deflection of beam is directly proportional to mass applied to the beam. Deflection of beam increases exponentially when distance from support to position of loading is changed.